Welcome to Calculus. I'm Professor Greist, and we're about to begin Lecture 13, Bonus Material. In our main lesson, we saw that perhaps the ultimate interpretation of higher derivatives is in terms of Taylor series, that if we are at a particular input, then the more derivatives we know at that input, the better we can approximate what the value of the function is farther away by some step h. It's a bit remarkable that just by knowing infinitesimal information at a particular input, that is, higher and higher derivatives at a, you can say what the function is doing far away. That actually goes fairly deep into other areas of mathematics. Let's take a few minutes and think a bit. In what follows, I'm going to use the language of operators, where, for purposes of this course, an operator is something that takes as its input a function and returns as its output another function. What are some examples of operators? Well, there's one that we've been looking at rather closely. The derivative, I'm going to give it an operator symbol as a capital D. Then what does capital D do? It takes a function f and returns the derivative df dx. Now, what's so special about this? Well, operators have an algebra associated with them. For example, we can take d and raise it to certain powers. We can talk about d squared as meaning we apply d twice. You take the derivative, then you take the derivative again. So the operator d squared is really taking the second derivative. D cubed is taking the third derivative. What is d to the 0? Well, that too has a name. It is called the identity operator and is given the special symbol I. The identity operator takes f and returns f. It does nothing. That is why it is called the identity. So d to the 0, the 0th derivative of f is, of course, f. What happens when we take powers of I? Well, I squared means do nothing, I, and then do nothing again. So I squared is equal to I. This might remind you of a number with which you're somewhat familiar. That is the number 1 under multiplication. 1 times 1 is 1. I squared is equal to I. This identity operator plays the role of the number 1 in the algebra that will follow. There are a few other interesting operators that we're going to take a look at. One, let's call it E, capital E. This corresponds to a shift of f. E of f is going to be the function which, when evaluated at x, gives you f at x plus 1. This has the effect of shifting the graph of f to the left by 1 unit. Now, what happens when we take e squared? That means shift to the left by 1, then shift to the left by 1 again. We can talk about e cubed, e to the 4th, etc. We're continually shifting f to the left. Now, can you talk about e raised to a non-integer power? E to the h. Well, surely that makes sense. We can simply evaluate f not at x, but at x plus h. And this means, of course, that we can talk about e to the negative 1, which we would call a right shift. Instead of evaluating f at x plus 1, it evaluates f at x minus 1. But note that this right shift, E inverse, really is the inverse of E. If I multiply e to the negative 1 times e, I get e to the 0, or the identity operator. And of course, this works whether I multiply e inverse by e or e by e inverse. This means that I now have a nice language for doing algebra with these operators. Let's see what happens when we think in this language for a little bit. What is e to the h of f evaluated at x? This is a shift by h. I need to take f and evaluate it at x plus h. Now, let's use our intuition from Taylor series. If I take the Taylor expansion of this, it is the sum, k goes from 0 to infinity, of 1 over k factorial times the kth derivative of f evaluated at x times h to the k. Now for the moment, let's not worry about where we evaluate this so much. Let's try to rewrite this in the language of operators. Now notice there's a kth derivative of f. So let's use our differentiation operator, d to the k, for taking that kth derivative of f. And now we see that there are two terms that are raised to the kth power, d, the differentiation operator, and h, this perturbation to the input. So if I collect those two terms together and say, I've got the sum, k goes from 0 to infinity, of 1 over k factorial times quantity, hd, to the k. I apply that to f and evaluate it at x. That is what this shift is. Now, step back for a moment and take a look at what we've done. We've really said that this operator, e to the h of f, is equal to the sum, k goes from 0 to infinity, of something to the k over k factorial applied to f. What is that? Where have I seen something like that before? This really looks like an exponential. But what am I exponentiating? I am exponentiating h times d, the differentiation operator, and applying that to f. If we remove the dependence on f, then what we see is that this shift operator, capital E to the h, is precisely the exponentiation of h times the differentiation operator. That is really a deep observation, that the shift E, just moving to the left by 1 unit, is I plus d plus 1/2 d squared plus 1 over 3 factorial d cubed, etc., etc. The shift is the exponential of the differentiation operator. Or, if you like, you can think of the differentiation operator, d, as the natural logarithm of the shift operator. Now, this probably is causing a little bit of surprise or confusion. What's going on? Well, don't worry too much. But think back to how this course began. We asked the question, what is e to the x? We will continue asking this question throughout the semester. What we have seen is that there are many responses to this question and many layers of understanding what we mean by exponentiation, what we mean by differentiation, and how derivatives conspire to give you deep information about a function.